I want now to think through the question of whether bar magnets are or are not dipoles. And in many ways they are. So if I start with the magnetic field from a bar magnet, here's my north pole, my south pole of the bar magnet, and if I just look at this pattern of field lines coming out, this sure looks a lot like the pattern of field lines from an electric dipole. For an electric dipole, we had a plus charge there and a minus charge there, and the field lines had this kind of shape. So in this sense, bar magnets are dipoles. They are the source of a magnetic field that looks like what we called a dipole field when we talked about electricity. Also, another way of realizing that they're similar is to think about a compass needle. If I have a little compass needle, and I put that compass needle here, it lines up with the magnetic field. So this is a tiny little bar magnet, otherwise known as a compass, and it feels a torque, and that torque lines it up with the magnetic field. If I put a little bar magnet here, it feels a torque that lines it up with the magnetic field. So the fact that bar magnets feel a torque that orients them with an externally applied field, that's the physics of dipoles. That's the physics of electric dipoles. And here it is for a little bar magnet, otherwise known as a compass. So that suggests that we should think of bar magnets as dipoles. Well, but there is a really important difference. And that difference comes about from when we try to make a monopole. Now, we didn't use the word monopole when we talked about charges, but we could have. Imagine that this is a plus charge and a minus charge, and I take this plus charge and I pull it way, way, way over here, far, far away, and now I have an isolated charge. That's what we started 802 with. We began 802 talking about single isolated charges. We didn't call those monopoles, but we could have. You take two monopoles, put them together, make a dipole. We never used the word monopole, but we could have. So let's do the same thing with a magnetic field. Let's take a bar magnet, which is, we just said it, sure looks a lot like a dipole, and let's bring this north pole all the way over here and isolate it. So how do I do that? Well, I take this bar magnet and I break it in half. I break it in half, and I've got now two smaller magnets, and I walk this one all the way over here, and then I discover that it didn't work because as soon as I broke it in half, I made a new south pole of this bar magnet here and a new north pole of this one there. So the fundamental difference between electric and magnetic fields comes about from the fact that with magnetic fields, there are no monopoles. There is no way to have an isolated north pole here with no other south pole anywhere nearby. That's impossible in nature. Now, nature didn't have to be this way. You can certainly write down a perfectly well-constructed set of equations that are a little different than Maxwell's equations that do have monopoles, in which there are isolated magnetic charges and isolated electric charges. That's not the world we live in. Experiments tell us that in nature, this is what happens when you break a magnet. When you break a magnet in half, you don't end up isolating just a single north pole, an isolated monopole of magnetic flux. What you get instead is a new smaller bar magnet with a new south pole at this other end. So let's look at the electric field of an electric dipole, the magnetic field of a bar magnet, often referred to as a magnetic dipole, and let's look at the similarities and the differences. So the similarities all have to do with the field at a distance. So if I start with the electric dipole and I walk my way around it at a distance, here there are electric field lines that are going in, electric field lines going in toward that negative charge, When I get over here, there's an electric field line going this way. Here there are electric fields coming out, electric field lines coming out, electric field lines coming out, and then when I get to here, there's an electric field line going this way, and then I get back to electric field lines going in. Now let's look at the magnetic field of a bar magnet, and it has all the same features at a distance. So here there's a magnetic field going in, going in, going in, going in, going in. There's a field going this way. Here there's field coming out, 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 and then there's a magnetic field coming back this way, and then there's field going in again. So at a distance, the magnetic field from a bar magnet or a dipole magnet looks the same as the magnetic field from an electric dipole. And this is why there are so many similarities in how they behave. Both of them will line up, an electric dipole lines up in an external electric field, A magnetic dipole will feel a torque that wants to align it with an external magnetic field. And the forces between magnetic dipoles are mathematically very similar to the forces between electric dipoles. So those are the similarities, and they all come about by looking at what the field does far away from the guts of the object. But now let's look inside the guts. And what you see here is that if I look inside the electric dipole, well, the electric dipole is made of two monopoles. It's made of two charges. There's a minus charge here and a plus charge there. And that means that inside the dipole, there's an electric field line going from the plus to the minus, going back this way. On the other hand, in the magnetic field of a magnetic dipole, or a bar magnet, if you look inside, what's happening is very, very different. This magnetic field line, instead of ending on a monopole, this magnetic field line just continues straight through. This magnetic field line continues straight through. All these magnetic field lines, in fact, continue straight through, and the magnetic field inside this magnet is going this way, whereas the electric field inside this dipole is going this way. And this is the fundamental difference between electricity and magnetism that I referred to a minute ago. Because in this case here, in the electric case, I can take these two charges, the plus and the minus, and I can separate them. I can walk this minus charge way, way, way over here, send the plus charge way, way over there, and then I have two isolated charges. The Coulomb's law that we started with describes the electric fields around them. I have an isolated negative charge here, isolated positive charge way, way over there. But that's not something you can do in this case. That's not something you can do in this case. If you break the magnet, as we discussed, what happens is you create a new north pole and a new south pole. There's no way of isolating one end of a magnet. Now, let's think about what this means for Gauss's law. So in the electric field case, what does Gauss's law tell us? Well, I draw some surface shown here by this black dashed line, and I do a flux integral all around that surface. I do an integral of E dot dA, electric flux dotted with dA around that surface, and doing that Gaussian flux integral tells me how much charge there is inside the black dashed surface. And in this particular case, we're going to get some non-zero answer because there's this much positive charge inside this surface. Magnetic case, let's take the same surface. Here's the same black dashed surface. And this time, I'm going to do the flux integral of B dot dA. So I'm going to integrate the magnetic flux instead of the electric flux. So I'll integrate B dot dA all the way around this surface. And over here, the magnetic flux is outward pointing. And over here, the magnetic flux is coming into the surface. And there's no monopoles inside here, no magnetic monopoles inside here. And so when I do the integral of B dot dA, I get 0. And so let me now say the same thing in multiple different ways. One way of saying this is if I break a bar magnet, instead of separating an N way over here isolated from an S way over there, I end up with, this N comes with a new S. When I break the bar magnet in half, I get two bar magnets. I get two dipoles. I don't get a monopole. Another way of saying it is that there are no magnetic monopoles in nature. In the laws of nature as we understand them, as we've discovered them from experiment going back to the experiment that predates Maxwell, we find this basic difference between electricity and magnetism, which is that in magnetism we find dipoles, but we don't find any monopoles. There are no isolated north poles in nature. It could have been otherwise, but as far as we can tell, many, many experiments have been done looking for monopoles. None have ever been found. As far as we can tell, the laws of nature are such that in our universe, with Maxwell's equations describing it, there are no magnetic monopoles. So that's the second way of saying the same thing. The third way of saying the same thing is that magnetic field lines never end. Electric field lines end all the time. They end when the electric field line goes into a minus charge. This is an electric monopole using our new language. Or they start when they come out of a positive charge. This is a electric monopole again. But there are no isolated magnetic charges. That means magnetic field lines can never end. Every one of these magnetic field lines continues forever, and in fact, every one of them is actually a closed loop. These closed loops, you can see the closed loop. These ones close down here somewhere. These ones close down here somewhere. This one that's horizontal might go half a mile that way before curving around and coming back around and closing. But every magnetic field line is actually a closed loop. None of them can ever end. That is another way of saying that there are no monopoles in nature. There are no isolated magnetic poles in nature. And then the fourth way of saying the same thing is this mathematical equation, that the flux integral of B dot dA is 0, not just on this surface, but on any surface. If I draw a surface over here, do the integral of B dot dA, 0. Do a surface over here, do the integral of B dot dA, 0. Do a surface right in here in the middle, integral of B dot dA, 0. Very different for the electric case. If I do an integral of E dot dA here, I get a positive answer because there's charge inside. Integral of E dot dA here is 0. Integral of E dot dA here, negative. There's negative charge inside. But in the magnetic case, if I do an integral of B dot dA, no matter what surface I choose, I will always get 0. And that is the mathematical way of saying what I said 3 other ways already. This equation is called magnetic Gauss's law, and it is, in fact, our second Maxwell's equation. So to summarize, what we have just seen is that if I take an electric dipole, I can easily cut it into an isolated plus and minus charge, which we didn't call monopoles before, but we could have. 2 isolated electric charges we can think of as monopoles, a plus charge and a minus charge. On the other hand, if I take a magnetic dipole, a bar magnet, and I cut it, I do not make an isolated N and S, I just make 2 new bar magnets. I make 2 new magnetic dipoles. So magnetic monopoles do not exist in isolation. That's a basic fact of nature, which is encoded in the second of Maxwell's equations, which is this magnetic form of Gauss's law, that the integral of B dot dA, the integral of the magnetic flux around any surface, is always 0. And this then, we are now at a point where we have 2 of Maxwell's 4 fundamental equations, and everything we do in the next part of 802 will be built on this second one of Maxwell's equations, of the magnetic Gauss law, plus the Biot-Savart law, which is the answer to how much magnetic field do I make at a given point P if I have some moving charge over here, plus magnetic superposition.